Hello there, my name is Sean Smith. I run the Integrated Materials Design Centre at UNSW Sydney. You'll see that the title of my talk today as a part of the Pawsey Supercomputing Centre Roadshow is Computational Materials Design, the Power and the Passion. So I think I must have been in a dramatic mood when I was thinking of a title for this talk. Basically, the power refers to the power of the compute engines, which the Pawsey Supercomputing Centre in WA and the NCI in Canberra provide for the Australian scientists. And then the passion comes from the scientists themselves who perceive, particularly when you're in my game as a computational materials design specialist, who perceive the amazing and truly remarkable possibilities that are opening up now with, through coupling the power of the computing with the power of the software for atomistic scale simulations. So that's in a sense the theme of the talk today, and I'm going to proceed on through now. This slide is a summary, if you will, of the, shall we say, the mode of operation or the philosophy of the way we do our research at the IMDC at UNSW. Essentially, the idea is to powerfully integrate the materials design loop, incorporating all of the major components that need to be brought together in order to drive materials design and discovery forwards. So this is not just computing and simulation, it includes materials synthesis, materials characterization, and materials fabrication and measurement and performance measurements. And so all of these different facets of the overall holistic cycle of materials design have to be brought together in a tightly integrated manner. And this is what we try to do at the IMDC. In a number of different spaces you see here: catalytic materials, electronic materials, soft matter and pharmaceutics, and energy harvesting and storage, which are areas of major strength at UNSW, which we've now built up the computational centre to complement and augment and accelerate. So that's the way we try to operate. I'm going to jump now into the first story that I want to tell you, which relates to charge modulation of the interaction of materials and molecules and reaction intermediates. We call it charge modulated electrocatalysis, as you see on the slide here. And I'll go back and give you a very brief history of where it came from. It started out, in my case, with a conversation I had with a professor at Seoul National University, Song-Kyun Kim, who was doing beautiful molecular beam experiments of the interactions between CO2 gas and azobenzene molecules. These are, like, as you see here, benzene molecules with the two blue atoms there are nitrogen, so nitrogen substituted into the benzene. And so you have periodic nitrogen in the benzene, and this molecule is interacting with CO2. And you do these experiments with multi-million-dollar pieces of equipment. You see all the stainless steel there. They're very sophisticated experiments in ultra-high vacuum, and use a laser to probe the details of the complex between the molecule, the benzene derivative molecule, and the CO2. And what you see, if you just allow these two molecules to interact with each other, is not too much. They form a very weak so-called van der Waals cluster, which is interesting in itself, but not exciting from the perspective of this story. What gets really interesting is that Song-Kyun Kim then bleeds in some electrons into the system, and he allows an electron to attach onto that azobenzene molecule, and suddenly his laser signal goes haywire. This was some 10 years ago now, I should say. He realized that, in fact, by adding one electron to that system, he had opened up a chemical bond between CO2 and the azobenzene molecule. So quite a remarkable response to simply the addition of an electron. And I went back to the University of Queensland, and I thought, well, goodness me, this is interesting, because we work with carbonaceous nanomaterials. These are carbon nanotubes or graphene materials and so forth, which can readily be doped with nitrogen, so that in principle we could get the same kind of periodic nitrogen doping into these carbon materials, and they're conductive. And so why would we not be able to implement this charging using electrical methods rather than doing it in a multi-million-dollar ultra-high vacuum system? And so this was the concept that's laid out in this little schematic here. Could we effectively be able to switch on an interaction with CO2 and grab it, capture the CO2 by application of charge, And then when we want to release the CO2 for sequestration or for subsequent catalytic transformation, we can switch the interaction off again. So it gives us a whole new lever for being able to control and modulate interactions of CO2 with particular materials, switched on and off by charging. That's the very simple concept that we started out with. And so I asked my postdoc at the time, Ai-Jun Du, who's now associate professor up at QUT, to start running some calculations and probing how this might work, and we got some very interesting looking results. So I'm going to now leap forwards in time, having given you a little bit of history. In the last couple of years, with the help of the Pawsey supercompute engines, we discovered a very interesting material, graphitic carbon nitride. We didn't discover carbon nitride, but we discovered this particular property of it, which, as you can see from the figure here, has lots and lots of peridinic nitrogen dialed into the structure. So in this case, you don't have to try to do ultra-high density doping. It's already in the chemical structure. That's how it gets made, with all of these nitrogen atoms which have just the same kind of behavior. And so we found that by charging this material, which has a very modest band gap of around 2 volts, you can switch on the binding of CO2 in this way. These are computational predictions which are suggesting experiments that can be developed. Okay? And so we got quite excited about that and published it, and and have continued down a pathway of trying to find fully conductive materials which have the same property and therefore would be easier to charge. And we have in fact found conductive materials with this kind of property. We also found, very interesting about the graphitic carbon nitride, as you see on this slide, is that by charging, negatively charging the graphitic carbon nitride, you also can turn on binding of hydrogen. And in fact, if you look at how many hydrogens you can load on that system when it's charged, you can get up around 6 to 7 weight% hydrogen, which is right in the target zone for the DOE's requirements for mobile hydrogen storage for automobiles. And so again, it suggests that not just CO2 capture, but potentially hydrogen storage for vehicles may be able to be modulated and controlled in this way. Now, I have to stress here, what's interesting is the modulation and the control. Because if you make a material, either it grabs hydrogen or CO2 very strongly, and if it does, that's good, but then you have to raise temperature very high to get it off again. If you make another material and it only weakly absorbs it, then you need very high pressures to get the gas on, so that doesn't help you either. Either way, you pay. And when you make a material in a lab, what you get is what you get. You don't really have much more control, much more ability to manipulate, unless you go back to the lab and make another material, right? Which takes time. Whereas here, we have a control mechanism. For any given material, we can modulate its interactions by implementing this charging protocol. That's why we think this is potentially an exciting nascent technology, shall we say. Just a quick summary here to acknowledge the team that helped us to get to where we are now with this. Xin Tan and Hassan Tahini in my team at UNSW, driving the calculations. John Zhu and his postdoc Xiaoyong Xu at University of Queensland, who did the early experiments. And Lisa Linson at UNSW Innovations, who's our business development manager. Thanks for your attention. I want to thank particularly the Pawsey Supercomputing Centre for the tremendous service they offer and the great capabilities that allow great science to be done here in Australia. Thanks.